Okay, hello everyone. Welcome to our second Cosmic Conversations talk. And today we have Dr. Partha Nandi, and he is a postdoc with Professor Stoltz. And he did all of his degrees at the SN Bose Institute for Basic Sciences in India. And now he's here at Stellenbosch, and he's going to tell us a bit about the work that he's doing.
Thank you. Thank you. Okay. Good afternoon, everyone. So I would like to thank the organizer to give the opportunity to present this my recent work. Okay. So, today I would like to discuss the kink of gravitational wave in a vibrating detector and emergent Berry Phase. So before going to detail of this discussion, so I would like to highlight the plan of my talk. At first, I would like to discuss some motivation regarding this aspect. Then I shall talk about some brief concept of Berry phase or geometrical phase in quantum mechanics. Then I will discuss some brief concept of linearized version of gravity and gravitational waves. Of course, I am not expert on this topic. Then I will discuss some interacting model with a harmonic oscillator system with the classical gravitational wave. Then I shall talk about the quantum mechanics of this interacting system, where the classical gravitational wave is still considered as a classical level. And then I shall talk about the adiabatic time evolution of the system and emergence of geometrical phase from gravitational wave interaction in Heisenberg picture. Then I will discuss some observation and conclusion. Okay. It is quite well known that the detection of gravitational wave in 2015 is one of the successful prediction of Einstein's general theory of relativity in weak level. And in fact, the gravitational wave observed, say, LIGO and Virgo, indicates that the detecting range of the gravitational wave frequency will rise between 5 Hz to 20 kilohertz, and it is reported in this literature. On the other hand, the frequency which lies below of this range is just considered as a low frequency gravitational wave, and the detection of this low frequency gravitational wave is one of the most challenging aspects in the gravitational wave observatory. In fact, in 2015, Lisa also proposed some of the point Rose gravitational wave frequency lies within this range, or say the less than of 1 Hz, will maybe detect through some sophisticated space-based interferometric experiment. This also reported in this latest literature. And the motivation to detect this low frequency gravitational wave is that the low frequency gravitational wave can be generated due to the supermassive, the collision or merging between the supermassive black hole at the center of galaxy. In fact, the other and the low frequency gravitational wave can also be induced from the cosmic strings at primordial black hole. So, in order to detect the basic motivation behind this detection of low frequency gravitational wave, the belief or hope is raised that if we detect the gravitational wave at a very low frequency region, then perhaps we can have some information, or we can decode the information of the early universe. That's the main motivation to detect the low frequency gravitational waves. And recently, Wilczek proposed some quantum theory of gravitational waves, and it's not experimentally tested. Now, in this talk, I will discuss some localized non-relativistic quantum detector, which is a theoretic at the level of theoretical model, which has some potential to capture the low frequency gravitational wave in terms of emergent Berry phase. So I will show you the Berry phase is nothing but the consequence of detection of gravitational waves. So before going to detail of this explicit concept, I would like to highlight the basic concept of adiabatic phase or Berry phase in basic usual quantum mechanics. So in order to appreciate the concept of geometric phase or Berry phase, there are many names of this phase. So let us start by considering a time-dependent Schrodinger equation, where the system Hamiltonian depends on a space variable and also depends on some set of external parameters which are slowly varying function of time. These are external parameters. Now, these parameters, set of parameters, are from a parameter space or called a real vector space. Now, since the system Hamiltonian exclusively depends on time, so we can't introduce the conserved energy. Since the Hamiltonian is not a conserved quantity, yeah. So we can't introduce the notion of constant energy. One can introduce the instantaneous notion of energy by introducing instantaneous state. So every instant one can introduce some eigenstate of the system Hamiltonian with specific eigenvalue. And this eigenvalue also depends on the set of parameters. Since the eigenvalue depends on the parameters, therefore one can immediately indicate that the eigenstate, also the instantaneous eigenstate at time t, also indirectly depends on this external parameter. So in other words, you can say that instantaneous eigenstate will be some element of projective Hilbert space. Now one can introduce the notion of normalized eigenstate at a particular instant of time t. Now the question is arise that suppose we consider the system at ground at some particular eigenstate at t equal to 0 or initial state. Now, what happens if we allow the evolution of this state? Now, suppose we consider the system at t equal to 0, find out in this particular state, and if you allow the time evolution, one can introduce the time evolution operator by usual the form of the time evolution operator can be introduced at the level of time dependent theory. Just since the Hamiltonian exclusively time dependent, so we need to mention the already Hamiltonian, so we need to some time order. Okay. So this is the typical form of the time evolution operator. So if you try to investigate the evolution of this initial state, initial eigenstate at time t equal to 0, how evolve with respect to this time evolution with this time interval t, small t. So since this time evolution operator is unitary operator, so therefore we can say that we produce some generic state of the same Hilbert space, and this state at time t can be written as a linear combination of the instantaneous eigenstates. Since instantaneous eigenstates form a complete set of bases, so any state vector can be written as a linear combination of these instantaneous states. And one can introduce this typical phase factor. This typical phase factor recognized as a dynamical phase factor because for time independent theory, it will give rise to the explicit time dependency of the state vector. Since we have a time dependent Hamiltonian, one can introduce a linear combination, the coefficient of itself time dependent. This will give rise to the probability amplitude finding a system in a particular state. Now, if we implement this above expression in this Schrodinger equation level, then one can arrive at this following expression. And this following expression indicates the rate of change of the coefficients. And this indicates that we have the two separate parts. First part of this expression indicates that the step-out probability or persistent probability amplitude for a particular state in K2. And this indicates that the transition probability amplitude. Now, this indicates that this transition probability based on this time derivative of the system Hamiltonian, matrix element of the time derivative of system Hamiltonian. Now, if you consider the system parameters or Hamiltonian depends on some time dependent parameters, and if you consider these parameters are very slowly varying function of time, then we can say the time evolution are slowly so that the system cannot jump from one particular state to other particular state. So one using this assumption, this is known as adiabatic approximation, and one can just get rid of this term and we arrive at a particular statehood or persistent probability. So if we start with this system particular in nth state, after time evolution, we just consider the system also be persist a particular nth state. There are no transitions. Now you can immediately observe that this object, the first term, is nothing but a purely imaginary term because the normalization constant clearly indicates is the normalization. So now if you take a time derivative, so you can immediately observe. So this in general may be a complex quantity. So this is nothing but a real part of the complex quantity. So this clearly indicates that real part completely zero. So these objects are purely imaginary quantity. So this object can be written in this following form, and one can immediately observe that using adiabatic approximation. So adiabatic approximation is the approximation which indicates the Hamiltonian change very slowly with respect to time, and so it does not jump one state to other state. And using this approximation, one can immediately arrive that if you start with the system for particular nth state at time t equal to 0, after time evolution, you immediately arrive at the same state at time t with this following phase factor. And one can immediately recognize this is the old phase factor, nothing but a dynamical phase because it explicitly depends on the energy and explicitly depends on the time evolution of the system. But we immediately recognize that one can implement some additional phase factor over and above this dynamical phase. So what is the nature of this phase factor? So Berry introduced in 1984 the system Hamiltonian which is slowly varying function of time. One can immediately implement some additional phase factor during the evolution of the state using adiabatic approximation. And the nature of this phase factor completely different from this usual phase factor because Berry also has assumed some other conditions. The condition there are two consistency conditions. One is the adiabaticity, and if you allow the time dependent parameter slowly varying periodic parameter. So if you consider the parameter space or periodic parameter space, so with certain periodicity which is capital T, T is the period of the parameters. So then after time evolution within the the particular period, so this phase can be written as in this following form. So in other words, you can immediately observe that this additional or usual dynamical phase explicitly depend on this time evolution parameter. So how system evolve with respect to time, this phase is more sensitive with this point. But this phase is not actually depends on the time parameter because it is just a derivative. One can immediately observe that this is nothing but just a one form. Okay. So, or in other words, it is completely, you can rewrite this above expression in terms of the gradient of parameter space. So, I want to say that we can rewrite this time derivative in terms of vector parameter space for some gradient of the parameter using this chain rule because the parameters are explicitly time dependent. So, one can rewrite this time derivative with respect to this gradient of the parameter space. So using this transformation or change of variable, one can immediately arrive at this following expression. And this following expression, since the parameter space form a closed loop under periodic evolution, we consider two conditions, adiabaticity and periodicity, and these two conditions we immediately observe this phase is nothing but a geometrical term because it gives the geometry of a closed loop in the parameter space. It's not explicitly depends on how state evolves with respect to time because it is not, it depends on the time evolution parameter. That is why it is called, this is the difference between this phase phase and this phase, because this phase exclusively depends on time evolution parameter t, but this phase is not exclusively depends on time evolution parameter. This is known as the geometric phase. And you can immediately observe that this is nothing but a flux through the closed circuit in the parameter space. So this is why this is known as geometric phase or so-called Berry phase. Now, let me introduce some basic concept of linearized theory of gravitation and gravitational waves. So let us start by considering Einstein-Hilbert action, which is nothing but a equation for, which gives rise to the equation for Einstein-Hilbert action and equation for Einstein equation. So now, if we consider, this is the equation for gravitation, this is the action for the gravitation is known as the Einstein-Hilbert action. And using the linearized approximation, so let us consider gravitational field as so weak. So you can split this metric in terms of the flat approximation and with some perturbation, which is called, which encode the effect of gravitation. Now, one can introduce this following observed object, which is known as the Christoffel connections, and the other is the Riemann constant. This is a very common expression, and using this linearized approximation, this above expression for action, Einstein-Hilbert action, can be written in this following fashion. It's quite non-linear. Now, this action enjoys two kinds of symmetries. One symmetry, which is nothing but a usual Poincare symmetries, that means the Lorentz plus translation part. And this action also enjoys some other symmetries, which is known as the gauge symmetries. So therefore, this action enjoys two kinds of symmetries. Now, in order to solve or in order to obtain the equation of motion corresponding to this action, one can immediately obtain the equation of motion for this action. And for this equation of motion, immediately observe that this is a complicated equation which is non-linear. So in order to solve this equation of motion, we have to put some restriction, and this restriction is known as gauge fixing condition. Since this theory has engaged on gauge symmetry, we need to spoil the gauge symmetry, and this common gauge fixing condition is known as transverse space condition. So in order to solve this h mu perturbation over and above this flat space-time, Minkowski space-time, one can introduce following condition. This condition is known as transverse condition, because this is nothing but these two condition is nothing but the counterpart of the Coulomb gauge condition in electrodynamics. And this additional condition is introduced because after introducing these two above conditions, we have still residual gauge freedom. And to remove this residual gauge freedom, we need to introduce this additional condition, the traceless condition. So therefore, in general, we have 4 by 4 symmetric matrix. H mu is a 4 cross 4 symmetric matrix. So where mu is run from 0, 1, 2, and 3. So any 4 cross 4 symmetric matrix has 10 independent properties. Now, the point is that this first equation indicates 4 condition because mu is run from 0 to 3. This second condition introduced 3 additional conditions. So 4 plus 7 is a 7 condition, and other is a scalar. It's only one condition. So we have 8 constraint or condition. So we have 2 genuine degrees of freedom. And these 2 genuine degrees of freedom can be interpreted as the polarization state of the gravitational field. And if you introduce quantization of this field, one can obtain the concept of graviton, which is spin 2 or polarization 2. So this is the main purpose of this linearized version of gravity. So after introducing this following gauge fixing condition, one can arrive at this simple wave equation, which can easily solve. Since this portion, you can immediately recognize this above 2 condition is nothing but divergence of A is 0 and A0 is 0. This condition. So now one can immediately observe that only spatial sector contribute. space time sector completely 0. Because mu is run from 0, 1 to 3, so only contributing term will be the spatial sector. That is some block diagonal portion of this 4x4 matrix will contribute. Now, since it is a periodic, since it is a wave equation, one can obtain some plane wave solutions, which is a periodic solution. And this immediately implement this transversality condition. This indicates that polarization tensor. So, the point is that since it is a rank 2 field, so it has some polarization implemented through some tensor. So, this is called the polarization tensor. And this polarization tensor will satisfy this following condition, and this is known as transversality condition. So, polarization tensor always affect orthogonal conditions with the direction of the propagation. Now, by choosing this following case condition, one can immediately observe that polarization tensor contributing only two independent terms. One is called plus polarization, other is called cross. And due to the traceless condition, it is nothing but a traceless Hermitian matrix. So, any traceless Hermitian matrix can be written in terms of Pauli's matrix. And also, it is a traceless. So, only Pauli, the 3 Pauli matrices can contribute, no identity term. Because identity and 3 Pauli matrices form a space or a 2 by 2 Hermitian matrix. Now, comment is that due to the transversality condition, H0 has non-zero component in XY plane. Only XY plane are contributing. Because if you consider gravitational wave propagate along Z direction, only perpendicular plane will be relevant for our discussion. Now, for this particular gauge fixing, one can immediately observe that H11 satisfy this condition and H12 satisfy this condition. So, this is the important remark for linearized gravitational waves. Now, if we want to see some physical effect of these gravitational waves, see, a single particle cannot feel any gravitational effect due to the Einstein equivalence principle. Because if you consider a single particle, if you consider the geodesic equation for a single particle, then geodesic equation you can immediately recognize that since it depends on this connection, Christoffel connection, and this Christoffel connection is a very bad term, it's not transformed like a tensor. So if you consider a particular frame was a local inertial frame, you can absorb apparently the effect of gravity. So in other words, you can say this equation is not gauge invariant. So you can absorb effect of gravity from the level of geodesic equation. So this point is that the gravitational, the single particle cannot feel gravitational wave. This is the effect of Einstein equivalence principle. So, in order to see the effect, non-trivial effect of gravitational waves or linearized gravitational field, we need to consider at least 2 particles, and we should consider the geodesic deviation equation instead of geodesic equation. Because if you consider the relative motion of the particle on the gravitational wave front, so to see the effect of gravitational wave, we need to consider 2 massive particles and measure the geodesic deviation between them. So this gives us the relative motion of particle in presence of gravitational field. And the concept of geodesic deviation gives rise to this following equation. And this equation is a good equation because this tensor is known as Riemann tensor, and this transforms like a tensor under diffeomorphism or arbitrary space-time transform. And it is a gauge invariant object. So you can absorb locally gravitational field, but it does not mean effect of gravity completely vanishes. The manifestation of effect of gravity will manifest in terms of the Riemann tensor. So that is why we need to consider geodesic deviation equation instead of geodesic equation. Now, so where Q is the relative wave vector between 2 geodesic, but geodesic is defined in terms of this x mu. So Q is the relative separation between 2 geodesics. Suppose you consider one particle for following geodesic line, so parametric by x mu. Now, other geodesics is just written as delta of x. Now, this separation delta of x denoted by q. Okay. So, you need to consider the relative separation between two geodesics. Now, if we implement transverse faceless gas condition at the level of this geodesic equation, and if you consider the test particle a very slowly moving particle, that is a non-relativistic particle, then 4 vector can be approximate in this following manner, and the proper time can be identified with the coordinate using this approximation. If you consider the moving particle are very slowly, okay. So this approximation, this is nothing but a non-relativistic approximation, one can immediately arrive at the simple looking form of this geodesic deviation equation. And this geodesic deviation equation, it just looks like a Newton's second law of motion. One can interpret the right hand side as a form of the force, and this force is known as tidal force. So at TT gauge, so the point is that the additional point one can make that the effect of gravity introduces some force law. Since this equation reminds us the nature of equation of motion for a non-relativistic particle, one can immediately rewrite this equation using transverse faceless condition, and this is the actual form of the equation. But the right hand side is the force law, and this left hand side we give by the definition of acceleration. This is the usual form of the Newton's second law of motion. Now we can consider at this point we have some equation of motion. We can reinterpret our geodesic deviation equation using non-relativistic and transverse faceless gas condition. We arrive at some equation of motion and reinterpret. This is our equation of motion, which has some effect of gravitational field. Now, and this describes the relative motion for two test particles. Now, if we consider very long wavelength approximation, so that is why the dimension of test particle very small with respect to the wavelength of the gravitational wave. So therefore, the plane wave solution, the spatial part of the plane wave solution can be approximate to 1, because k is related to the wavelength of the gravitational wave, and x is the position of the test particle and can be approximated dimension of the test particle. So since the wavelength is very small, very large, so this phase factor is very small, so it is sufficient to work with the first term of the exponential series. So it is approximate to 1. Now, since we have considered the long wavelength approximation, so therefore the plane wave solution in general function of space time, because there is a field which is to the power I and t. Now using long wavelength approximation, if you approximate, it is only function of time. So therefore, for long wavelength approximation, gravitational field can consider as only function of time. Now we arrive at some time dependent, explicitly time dependent gravitational field, which is a periodic function of time because it satisfies the wave equation. And if you consider the mass of the test particle is just m, so you can immediately observe that this is the equation of motion for the test particle, which describes the relative motion to test particle. This is the relative motion of test particle with mass m lying on the gravitational wave front. Now we ask the following question: Can we derive this equation of motion from some Lagrangian? Usually, we have some Lagrangian. Suppose we have some Lagrangian, one can immediately derive the equation of motion by using Euler-Lagrange equation. But ask the inverse question: given equation of motion, can we introduce some Lagrangian? So, using Feynman inverse problem technique, one can immediately observe. As we have already mentioned, this right hand side is nothing but the effect of tidal force. And Okay, before going to discuss the formulation of Lagrangian corresponding to equation motion, so far we have discussed two free particles feel the effect of the gravity. This is the relative motion of two free particles. Now, the right hand side implement the effect of gravity. Now, suppose instead of two free particles at non-relativistic level, we consider a spring where two particles connected by spring with particular spring constant. So there are some mechanical force term apart from this gravitational force term. So we introduce some mechanical force term which is the oscillator term, because we consider two test particles. Now instead of completely free test particles, consider a test system connected by the spring with spring constant. Now consider spring constant are slowly varying function of time, or in other words, you can say the spring constant are varies, or frequency of this potential are very slowly varying function of time instead of static frequency. There are some reasons to consider this frequency, time dependent. I will discuss the reason behind this considering this time dependent frequency very slowly varying. Now, one can interpret this equation and nothing but equation for a test particle. So you can draw a diagram of this equation. So just consider a test particle with mass m, test particle with test particle with mass m, connected by a spring, lying in xy plane, and now allow the gravitational waves to propagate along z. This is the schematic diagram for the model. So you have a system of harmonic oscillator placed in xy plane. Now gravitational wave propagate along z. What happens? Now ask the following question: what is the corresponding Lagrangian from where one can derive this equation of motion? Because we want to develop the quantum theory of this interacting system, we need some Hamiltonian. So before going to discuss, or before postulating the Hamiltonian, we need to understand what is the Lagrangian. Then one can, using the transformation, one can obtain the Hamiltonian. Now, using inverse problem, one can immediately recognize that if you consider this Lagrangian with this following structure, using Euler-Lagrange equation of motion, this will satisfy this equation. Of course, this is not a unique Lagrangian, okay? Because you know this Lagrangian differ by total derivative. So this is the one of the Lagrangian which satisfy this equation. Any physical effect does not hamper with this total derivative. So therefore, we just consider this Lagrangian, but this Lagrangian indicates some common thing. This Lagrangian, or in other words, you can say, if you have this Lagrangian, one can use the linear transformation, or introducing canonical variable, one can implement this Hamiltonian corresponding to this Lagrangian. Now, this Hamiltonian reminds us very common expression for a system. The system is when a charged particle moving in uniform magnetic field, the expression for momentum is called mechanical momentum. If you have a charged particle in presence of magnetic field, then we just need to shift. P goes to P plus EA by C. This is known as mechanical momentum. Now, this is the expression. This object is known as magnetic vector potential, or sometimes known as the electromagnetic connection. Here, instead of electromagnetic field, we consider the gravitational field. So therefore, we immediately arrive at this form, which is closely analogous to this form. And one can immediately observe that this object here is nothing but a gravitational connection, which is called Christoffel connection. We have this Lagrangian, we have this Hamiltonian. Now, we will move on to discuss quantum theory of this interacting system, where the interacting system denoted as oscillator with gravitation. Now, in order to appreciate this interacting system at the level of quantum mechanics, we just elevate our S-space variable at the level of operator. but gravitational wave still considered classical. Just like a Landau problem, electromagnetic, you are in a charged particle moving in a magnetic field. Magnetic field still considered as a background field, but the charged particle is considered as a quantum mechanical particle. Now, the corresponding Hamiltonian also can be implemented at the level of operator, where Q is the degrees of freedom for relative motion of two test particles, and P is the corresponding canonical momentum. However, P plus something, this thing, is not a canonical momentum, it's called mechanical momentum. However, they are commuting each other. The basic contradiction is that in electromagnetic case, these objects will not commute each other. This will give rise to some proportion to magnetic field. If you calculate this commutation at the level of operator, phi by phi j, it will proportional to f I j. But here, f I j is just a dual of the magnetic field. Now, here this object P plus this thing will commute itself because gravitational field are an symmetric field. Okay, this is the point. Now, if we introduce this basic canonical commutation bracket, now the interpretation of this Hamiltonian, the lesson of this Hamiltonian is we are interested to study the effect of classical gravitational wave at the level of quantum detector, where the detector, our detector or model detector at the theoretical level considered as a two particle system connected by speed. Now, this can be rewritten in this following fashion. One can immediately observe that gravitational wave introduce some additional interaction or additional term at the level of phase-space variable. So, interpretation of this Hamiltonian is that now the Hamiltonian can be reinterpreted as a system Hamiltonian which is excessively time dependent. The time dependent is a two part. One part is coming from the interaction of gravitational wave, which is by default is a function of time for long wavelength approximation, and itself a periodic function of time because it satisfies the wave equation. And we introduce a time dependent frequency by hand. So this is the artificial time dependency because it depends on the nature of this detector. But this second term is not our choice. It is just natural consequence of the interaction of gravitational wave and oscillator. So now you can reinterpret this is a time dependent oscillator, depends on some external parameters, where the parameters, one of the parameters depends on this gravitational wave amplitude or gravitational wave interaction coupling constant, and other parameters is a spring constant. So you can interpret this Hamiltonian as a time dependent Hamiltonian explicitly depending on some external parameter, and if you consider this term Hij dot T for low frequency gravitational wave interaction. For very low frequency case, since the frequency is very small, the time period of the wave is very large. So, large time period means this change very slowly. So, this is the part of adiabaticity. So, adiabaticity can be implemented at the level of low frequency gravitational waves. Now, omega square T is our choice of parameter. Now we consider the omega function of T is also a time dependent parameter which are also slowly varying function. So we can recast this Hamiltonian at the level of adiabatic variation. So we have the system Hamiltonian which is slowly varying function of time. One part coming from the gravitational wave interaction. If you consider gravitational wave is very low frequency, because the then time period is very large, then the variation of this parameter is very slow. And other is our choice of parameter, which we choose some parameter which is slowly varying. It's now since the gravitational wave interaction Hij, as we have discussed, it is a 2x2 traceless matrix. You can rewrite in this following fashion and in terms of sigma 1, sigma 2. Because any 2x2 Hermitian matrix is traceless, If it is Hermitian, real Hermitian, then only sigma 1, sigma 3 contribute. Because sigma 2 is a complex Hermitian. Now, this expression already given in the textbook by Messner Thorn Wheeler, where the chi t is known as the amplitude of chi t is the time dependent portion which encodes the information of low frequency and the amplitude of the gravitation, and itself a periodic function of time. Now, the important point is that here you consider, please note that here you consider the order of adiabaticity. Each time dependent parameter are same. That means the rate of change of this parameter, rate of change of this parameter, order of the rate of change of this parameter are same. This is the condition. Or you can say you can adjust your time dependent frequency now, because you can't adjust this frequency. It is a natural consequence, because you consider the low frequency gravitation rate. It has certain adiabaticity. Now you adjust your oscillator frequency in such a way that the rate of change or order of adiabaticity of this frequency will consistent with this order of adiabaticity of this parameter. So all parameters should consistent with the same order of adiabaticity during the variation of time. Now, let us introduce some useful phase space variable, which is a canonical phase space variable, or say canonical transformation, by using this following operator. After introducing this new phase space variable, one can rewrite this old Hamiltonian in this following form. And one can immediately observe that this Hamiltonian contains interesting two terms. These terms are scale invariant time universal symmetry breaking term. It's called dilatation term. This term and this term. So therefore, this indicates that two modes of this oscillator individually interact with gravitational waves. The modes are not interact each other. Two independent modes interact individually gravitational waves. There are no mutual interaction between the modes of the oscillator. So you can treat them to independent mode. So one can consider this is a two-dimensional oscillator with additional interaction, time-dependent interaction, where gamma is the again periodic function and depends on the gravitational wave amplitude. Now, in order to obtain the eigenvalue, instantaneous eigenvalue of this system Hamiltonian, one can introduce this following notion of ladder operator. Just when you derive the harmonic oscillator in terms of ladder, we need to introduce some ladder operators. So, if you introduce this definition of ladder operator, we satisfy following commutation bracket, and also introduce some Hermitian conjugate of this ladder operator, annihilation and creation, one can immediately observe this above Hamiltonian can be rewritten in the quadratic Hermitian form or written in the number operator. So using this form, one can immediately read out the instantaneous eigenvalue and instantaneous eigenstate, because it is a common form of the harmonic oscillator Hamiltonian, where this omega is the effective frequency which satisfies following conditions, since the omega star should be positive definitely. So this indicates the oscillator, the natural frequency of our system oscillator should be greater than with this gamma square, 4 gamma square. So this introduces some bound over the oscillator part of the Hamiltonian. Now, using the concept of Berry phase, as we have discussed, consider we have the parameter space depends on two time dependent parameters, beta and gamma. Beta is the frequency term, this, and gamma is the gravitational wave interaction term. So the Hamiltonian change via this parameter in a manner that it makes a circuit in the parameter space, because you consider gravitational wave itself a periodic function of time, this psi, and we consider by hand omega itself a periodic function of time with same period. So therefore, under a closed cycle, or closed or time evolution with this period, we arrive at some closed circuit in the parameter space. Now, if you introduce the time evolution equation for ladder operators A1 and A2, if you consider the equation of motion for Heisenberg, this is called the Heisenberg equation of motion for some time dependent operator. So we arrive at this following equation, and one can exactly solve this equation because it is the first order differential equation. So one can exactly solve this equation, but since our time dependent parameters are very slowly varying function of time, we need to work with some first order operators. Only approximate solution will be enough to discuss the effect of new phase. So if you solve this coupled differential equation using adiabatic approximation, after some little algebra, you can immediately arrive at this following structure. And this following structure, one can introduce that this term is nothing but our dynamical term, which depends on the explicit time, which depends on the time evolution parameter t. But this term, this dt and dt will cancel, and it is nothing but our explicit time independent phase. So this phase recognized as geometrical phase. So after time, so this is the way to understand how gravitational wave introduced the geometrical term, because this gamma incorporates the effect of gravitational wave. Because we have already mentioned the expression of gamma, it depends on the polarization part and the amplitude of the gravitational wave. Now, after using the equation of motion of this ladder operator, and if you solve up to first order of adiabaticity, one can immediately arrive at the solution of this ladder operator in this following fashion. So there are two phase factors. First phase factor is.
So can you quickly show the expression for omega again?
Yeah. This is the omega. You see, separately we can focus on this term only, because this term is not explicitly time dependent. Sorry, this term is not explicitly depends on this integration can be derived as a parameter, I mean the closed integral in the parameter space. But this integral cannot be derived as a closed integral in the parameter space because it explicitly depends on the final time period, final time. But this does not explicitly depend on the final time or upper limit of this integration. That is why you can rewrite in this following form. And this factor is purely geometrical because it gives rise to the concept of flux through this circuit gamma in the parameter space. It's nothing but a flux, where you can imagine, you can recognize this is the vector potential, one form. This is nothing but integral of one form. Okay, and this gives rise to the flux. Now, this line integral, closed line integral, indicate remarkable observation. The observation is that if you switch on gravitational wave interaction, that means if you switch on this gamma, this term completely vanishes. Because it depends on the gamma, variation of gamma. If you switch off this gamma or switch off the gravitational wave interaction, this additional phase factor will not contribute, only dynamical old term contribute. There are no new thing. But if you allow the gravitational wave interaction, which is slowly varying, or in other words, if you allow to interact low frequency gravitational wave with a model detector, suitably designed model detector, then you can arrive at seeing this additional phase factor over and above this dynamic factor. And this is purely gravitational wave induced. Otherwise, not is only depends on the gravitational wave induced term, there are some important other observations. See, this omega. What is the expression for omega? If you notice carefully, this is the omega, expression of omega. Now, if you again switch off the time dependency of this small omega, or say natural frequency of the mechanical oscillator are time independent, then there are a problem. Again, this phase will be zero because if you is our phase factor. Since alpha is time independent term, you can pull outside this integration. So the only relevant term is 1 by omega. In fact, alpha will cancel each other. We artificially derive in this following fashion. Alpha itself cancel. This is just now, what is the form of omega? It is just omega square minus 4 gamma square, and this is just d gamma. You can rewrite this in here in this following form. Now, if you switch off the time dependency of omega, you can rewrite this object as a total derivative of something. And since you consider it cyclicity condition, the initial limit or lower limit and upper limit, the integral will take same value, they will again. So that is why we need time dependency of the frequency term also, along with the gravitational wave. Otherwise, this case cannot be recognized. So this is the joint effect of time dependency of mechanical oscillator with low frequency gravitational wave. Otherwise, you can't recognize this phase because it's trivially zero. That is why we need the time dependent oscillator, okay, to recognize this phase or recognize this new effect. Now, this phase is one can immediately interpret the geometrical phase, and using Stokes theorem, one can again convert this closed circuit to a surface integral. And this term is nothing but daily curvature, because when you have a line integral of one form, you can use Stokes theorem, you can derive this d of a, where d of a is a curvature. Now, this is the two form. I don't know whether you are familiar with your form convention. Anyway, this is the you can simply say you can derive this line integral in terms of the Stokes theorem. You can say this is nothing but just like a dot dr, just a Ampere Salpeter law, you know, the a dot dr can be written as curl of a dot d. So curl of a is just a field. So that is why this recognized as a curvature of the parameter space. So this indicates that in presence of gravitational waves, low frequency gravitational waves, and the time dependent frequency of the mechanical oscillator, effective parameter space is some sort of curved space, which make a solid angle subtend in the origin. And this solid angle is this space. Just like if you consider the S2 or sphere, you can just consider the Hamiltonian, the famous Hamiltonian is called B dot or sigma dot B, function of time. But B is the magnetic field, time dependent magnetic field. And this is the spin interact with the spin magnetic moment when interact with magnetic field. This is the interaction. Then, if this is the tip of this magnetic vector, and if you rotate around a closed circuit, this will give some spherical cap, and the subtend a solid angle in origin, and this will give rise to some phase for this Hamiltonian also. So that is why in this in our situation, the structure of Hamiltonian is completely different. But I want to mention that our parameter space is non-trivial parameter space. It is not a genuinely flat parameter space. It has some curve. Okay. This is this case indicate the notion of the geometry of parameter space. Now, observation. The key observation of our analysis is that if we consider both polarization, simultaneously. Plus and cross. This gamma is non-zero, and we have non-trivial phase. And if you switch off one of the polarization, suppose if you switch off plus polarization, contribute only cross, or in other words, if you switch off the cross polarization, contribute only plus, then phase also contribute, because the expression of gamma is the expression this. This expression depends on the linear combination of cross and plus. If one of the term will survive, then phase will continue. This is the point. So this is a purely gravitational wave induced phase. Okay. So thus we can say that our geometrical phase is nothing but a hallmark of both type of polarization of low frequency gravitation. Now, other observation is that how one can predict a system Hamiltonian has some will provide geometrical phase or not. By observing a system Hamiltonian, one can say they can produce geometrical phase without calculating anything. So there are two important issues. The first issue is that in order to obtain the geometrical phase, if we go back to our previous slide, I introduce this term. I have mentioned that this term is the origin of this geometrical phase. Now we have introduced this term will be purely imaginary term. This term will be purely on imaginary if and only if the wave function corresponding to this state is a complex. Okay. Now if you consider a system Hamiltonian which has discrete non-degenerate state, so every state must be real, because non-degeneracy cannot allow complex wave function. So this is the point. So because the non-degenerate bound state in one dimension must be real. That is why every ground state of system are real wave function, except a charged particle in magnetic field. Every ground state, if you consider any ground state of any problem or ground state problem, ground state always real. Ground state wave function always real, except charged particle in magnetic field. Because of this. Now the point is that if you have discrete non-degenerate state that corresponding to this state, and if you observe this state contribute Berry phase, this only wave is state corresponding wave function of this state should be complex function. And in order to obtain complex wave function at the level of non-degenerate state, the system Hamiltonian should break time reversal state. This is the point. So if you have a system Hamiltonian which spoil the time reversal symmetry, the breaking of time reversal symmetry is the sufficient condition to obtain geometry. Not necessary. Then what is the necessary condition? In obtaining geometrical phase, oh, okay, fine. I will finish soon. Okay. The necessary condition is that the system Hamiltonian, one can immediately recognize that this system Hamiltonian can be written in terms of the SU11 group generators. So now, if you have system Hamiltonian which can be written in terms of any arbitrary group generators which complete the algebra, Lie algebra, then this system Hamiltonian can introduce geometrical phase. So this is the necessary condition. So those Hamiltonian which can be rewritten in terms of the group generators which complete the Lie algebra, then this Hamiltonian can introduce the geometrical phase. And this observation was first made by Robert Gilmore in this following part. This is a group theoretical understanding of geometrical phase. Now, since our investigation based on the Heisenberg picture, now one can move from Heisenberg picture to Schrodinger picture, just usually making some unitary transformation, and one can immediately observe at the level of Schrodinger picture, our state also acquire this additional phase factor. This phase factor can be split into dynamical term and geometrical term. Since one can immediately observe these independent two modes, geometrical term for first mode is positive, sorry, negative, and geometrical term for second mode is positive. So two modes have two opposite sign of geometrical phase. That is why when you rewrite the geometry or implement geometrical phase at the level of Schrödinger vector, you have the different sign. This is the point. Now, this emergent geometrical phase may be detectable in principle, but we are still far from the qualitative. Now, we can consider some quantitative argument. The quantitative argument that if you consider our detector just like a LIGO detector, then the end point of each arm, because the LIGO detector based on two arms, two mutually perpendicular arms. So if you consider your detector, just a very rough picture. Say this is the arm 1, this is the arm 2. And if you consider the end point of each arm, as a free part, as a point particle, and allow to vibrate each arm. There are some mechanical vibration. If you allow some mechanical vibration of individual arms,